talk about how we discovered the side channel in secure message transmission. So this is joint work with Majid, Ghaderi. I think I should press this one. I don't know. Okay. Majid, Ghaderi, Sam, Jero, and Okhravi from MIT Lincoln Lab, Cristina, Nita-Rotaru from Northeastern University. Okay, so just go back again. And Majid and I are from University of Calgary. Okay, so the basic problem is the problem of secure message transmission. So Alice wants to send a message to Bob, and there is the channel is eavesdropped by an adversary, and the adversary can be active, can be passive, but it is access to quantum computers, so it can do any computation that is, well, that are doable by quantum computers and even beyond that. So because we are looking at information theoretic security. So in this setting, the way that we do secure communication is either we establish a shared key and then encrypt the message using the shared key. So that's one way of doing it. The other way is to just directly encrypt the message. And when we say directly encrypt the message, either it would be something like using a public key crypto system or physical layer security assumptions. For example, we can have a wiretap channel that assumes that the adversary has a noisy view of communication, and that is used to establish use randomized coding to have secure communication. So encrypt is a kind of, encrypt is a kind of general term that I use for both public key encryption and also the kind of encryption that comes with physical layer assumptions. So in all of this, when we want to have security, we need to have some assumptions. And the kind of assumptions that we have are either a hardness of some mathematical problems. So this is what is very familiar to us. And now we are having all these assumptions that are, at the moment, do not have any efficient solution. Quantum computers, we can use those. Or we can use quantum theoretic assumptions, things like QKD, and that gives us secure communication. And finally, we have physical layer assumptions. So in this talk, I'm going to talk about, the talk is going to be on physical layer assumptions. So a model that uses physical layer assumptions. So the outline of the talk is going to be, I'm going to go through this model of secure message transmission, which uses physical layer assumption to provide secure communication. Then I look at introduce this moving target defense, which is a version of, which is based on secure message transmission, but tries to make it practical. And then argue that we need to have this implementation of this NTD. And when we do this implementation, the kind of failure that we have to try to achieve our research goal. And finally, how we came up with this, looking at all these experiments and the failure that we had allowed us to find this new side channel attack in these systems. And then some concluding remark. Okay, so this is the model of secure message transmission. This is introduced by Dolev, Dwork, Wartz, and Jung in 93. So this is the way that we model a network. So a network which is partially corrupted by the adversary can be modeled as a set of no disjoint path between sender and receiver. So we forget about all the details of the network and we say that there are 3 paths between Alice and Bob. So that's the abstraction of the network. And then this adversary can be only passive adversary, it can be blocking adversary, it can be Byzantine adversary, depending on or it can be a mix of these. And so the resource that these two have, the Alice and Bob have, is the multiple path between them. And the assumption is that the only K of these paths are corrupted. So the adversary can get access to a subset of this path So that's the limitation of the adversary. Security is defined, so we define both security and reliability. Security is going to be by requiring the statistical distance between the view of the adversary for any two messages is going to be negligible, so distinguishability best security. And then reliability is the probability that the receiver can recover the message that was sent. So as you can see, there is no shared key. This is purely the resource of the communicants or these multiple paths. So, and the way that we send the message is through randomized coding. So this is an alternative to Shannon's model of perfectly secure communication that uses a shared key. Here we do not have a shared key. We rely on this kind of multiple path, and we have the same information theoretic security that we have in Shannon's model. So, so this is for security, and we also look at efficiency. Efficiency is effectively the number of bits that need to be sent for one bit of information, which is our message. So, and as the motivation of this model came from starting from multi-party computation that we have in not fully connected networks. So we wanted to establish fully connection between every two nodes in the network to provide full connectivity. We use this model of secure SMT to establish a perfectly secure link between every two nodes in a multi-party computation. So the motivation was theoretical, but then because it's a nice model, it has also found a lot of application. A lot of multi-routing protocols have been using this model of network. So these are some of the people who have worked. You can see quite a list of eminent cryptographers. They have done work, and it's the interesting part is that it is both on the theory side and also on the practical side of things. So if again, one of the interesting results is that when you look at the work, the result that we have, so the important point to note in terms of efficiency is how much connectivity you need to have. So how many corrupted wires, so we call them, each path is also called wires. How many corrupted wires can you tolerate? And you can see that in both in case of secure transmission and if you only require reliable transmission, the numbers are similar, the same. So in both cases, if you need a one phase, which means one message, perfectly secure message transmission, you need you can have up to a third of the lines to be corrupted. And if you do allow to have more than one phase, so you have interaction between sender and receiver, you can tolerate half of the lines to be corrupted. And if you do allow to have epsilon delta, if you give up on perfect security and perfect reliability, you can tolerate half of the lines to be corrupted. And also you have this kind of bit efficiency. You can see also the results are very similar. So really, in fact, so reliability becomes a bottleneck of this system. So, but you also need to have perfect secrecy, and that also creates a lot of challenging questions and a lot of nice coding theory construction to achieve both of them in minimum number of rounds. So if you look at the work, there are a lot of very, as I said, elegant protocols that are interactive. They have a complex encoding and complex decoding that makes them very hard to use in practice. So our goal was to do take some of these theoretical results to practice. So if you want to do that, then you have to accept some of these simplification that you need to have, because other than that, the protocols are too complex, and no one in practice accepts many rounds of back and forth to send one message. So the protocol, we are going to limit ourselves to single phase, and then we have epsilon perfect delta security. As we start with passive adversary, and passive adversary is also justified because Because in all these APT, advanced persistent threat that you have, the adversary is dormant in the system. So you do want to have, you can assume that the adversary is passive and it just wants to collect information. So this kind of analysis actually does make sense. And then, yeah, so we also, if we assume that between Alice and Bob, there are hundreds of node disjoint paths, they do not need to use all of them. So a subset of them is going to be enough for communication. So once you do put all of these together, you will have this kind of system that you have, which we call path hopping, so it's, or moving target defense. It falls into that category of system. So Alice and Bob, they have all of these lines between them, paths between them. For each message, Alice is going to randomly choose a subset of path. Bob can also choose a subset of path in the same round. If he's lucky, he's going to get this message. So that's the model. So for every message that comes, Alice is going to choose a different set of path. And the adversary also has a chance to choose its own set of path. So to analyze such a system, we need to look at this kind of, there was a framework for MTD, so moving target defense, that we followed that framework that models this system as a Markov game between Alice and Bob, so both of them with random strategies. So you have the state of a system is going to be expressed by this kind of, by a matrix. So this is a transition matrix for the Markov chain or Markov model that we have. And this is a combination of the movement of defender and the movement of attacker. And these are the probabilities of in each time slot for each message, whether the attacker, whether the defender decides to change this subset or is going to stay with this current subset. So these are the probability of them moving or staying where they are. So once you do this kind of thing, you can have a Markov game, which is a fairly simple Markov model, and then the state of the system becomes the number of paths that the adversary has captured. And so when it captures k of these paths, then the system, so if we assume that the encoding that is used is a k secret sharing scheme, which basically means that a message is broken into k shares, and all k shares are required at the receiver to be reconstructed to reconstruct the message. If we assume that is the coding, that's the basic coding that we are going to use, then the winning state of the adversary is going to be the state k, where the adversary has collected all of the k shares. So when we do this analysis, this is a simple, for the simple case that in each time slot, the game is when the defender only changes one of the paths. If they have k paths, they are not going to choose all of them. They're not going to change all of them. They're changing one at a time in each time slot, and the same case for the adversary. The adversaries also have changing one of them. This is just an example. You can have, in general, you can have any number. So this, the game that we have can work for adversary, any number, the defenders changing any number of paths for the message, and the same with the adversary. So once we do this, once we do this kind of modeling, then we have these two measures for security. So one measure of security is the expected number of compromise in the first t time slot. So these are new measures that we are introducing. So this is, one of them is this one. The second one is expected number of steps to the first compromise. So these are the two measures of security that we have. We want to see when the system is dynamic and evolving, how many times the system is going to be compromised in the first t time slot. So when, I think this one doesn't work. Maybe this one's running. Okay, sorry, it works. So when you graph this system, what you will see that, so you can obtain this, you can show these theorems fairly easily, not with much problem. So these two measures can be derived from your Markov model. Markov matrix that you have, or transition matrix that you have, and when you graph it, you will see that if the defender moves, the higher, the more likely they are to move in each time slot. If the higher probability of moving, then the security increases. You can see that the number of times that the system is going to compromise decreases. Similarly, the amount of time that it requires for the system to be compromised increases. So really, it looks like the faster the defender move, if they move their subset of wires that they choose, in every time slot, the system is going to be more secure, which is also intuitive, because if we change more, we expect to be more secure. But then this modeling is lacks an essential ingredient, which is the cost of moving the path, changing the path. So this is a very abstract model. It doesn't consider that. But in reality, every time that you change a path in the system, you have to reprogram your router, your switches, and you have to make sure that the messages that are in the system have arrived. So there are a lot of things that really limits the speed of changing the path. So, and that is what we thought, that our analysis does not capture what is happening in real life, and it's not just looking at the bit efficiency is not a sufficient measure. So that is why we wanted to have we thought this is necessary. Without we haven't done a proper modeling if we do not capture the costs of or delay that we have to consider when you hop a path. And the question becomes what to implement and how to measure. So what are the things that we can measure and what to implement? Just remember that the abstract model are just wires. And so we have to somehow translate this wire model in real life system. So that is where our collaboration with our networking and system groups in these two institutions, Northeastern and MIT Lincoln Lab, came into being. So we have started working together to understand that how we should model this thing, and what sort of, how we can estimate the cost so that we can refine the model and get a meaningful theoretical result. So that was our goal. So this is the theory. The model looks like this. So between Alice and Bob, there are just these wires, and then the adversary corrupts one of these wires. But if you go to real life, in practice, so when we talk to our networking colleagues, they just say, okay, so how should we implement a wire? How do we interpret a wire? And so a wire in real life is a set of nodes, and they're connected by links. And so in a first degree simplification approximation, we can say all of these links have the same delay, introduce the same delay, so we can ignore that, but still there are some of the paths are shorter, some of them are longer, but so this distinction exists. And then now we also have this, the question is that, okay, where is the place that the attacker is going to compromise the network? Is it going to be on the nodes or on the links? So this was also a discussion that we had to discuss. So we ended up with a model like this. So we said that we started with a very basic encoding of breaking the message into K shares, and there's a KK secret sharing scheme, and then doing the sending each of the shares on a path. And the nodes are places that the attacker can compromise the system. And yeah, so I think that's, and we assume that the attacker can access all the nodes in the system. But at each time, it compromises K nodes. So that, and the research goal was to see what is the cost of, how much delay we need for this system to work properly, in the sense that if we hop too fast, we may lose some of the messages that are sent, and the reconstruction rate will become will be affected. So we wanted to avoid that. So the first implementation that we had was using software-defined networking. So in software-defined networking, you have a controller that calculates the paths and then sends it to switches, and switches are just doing the data transfer. They are not doing any thinking. So that's a model that is used in both in data centers and also in small networks, which is quite a popular and realistic model to have. So that is what we did, and we tried the Mininet implementation for that is to emulate the network, and it was like a 2-year work. So the interesting part, the first round of the first try of implementation, we actually did obtain these delays that's for controllers to calculate the path and distribute them and the network to work. But then in a better implementation that our networking colleagues came up with, in a much using proactive routing and new methods of routing in protocol, they could completely remove that cost. So it seemed that we do not have, actually, there is no cost in using this multipath hopping. So you can do as fast as you want, it's negligible. So it seemed it was counterintuitive because we thought there is a delay, and when you think about network, you immediately think about internet. So in internet, this is not internet, this is software-defined networking, which is a valid networking technology, and in that setting, you do not have any at least in this software implementation, there was not any delay. So that motivated us to look at the physical layer, physical implementation. So we bought switches. We established a 20-node network on real switches, real-life switches, and so the state-of-the-art switches, and repeated the same implementation, and again the same thing because again we failed. We could not measure any cost because of the network was too small and switches were too fast and too advanced. So we couldn't get any cost in that case either. So that was a bit of disappointment. So we didn't get what we wanted. We couldn't measure any costs, and after two years of work. So at that stage, our colleagues in networking and the system were quite interested in the model. They're really arguing that this is a very nice model. You can use it for secure transmission in network. So we just have to show this is practical in practice, although it has a big redundancy in terms of you have, instead of one message, you send effectively K pieces of information of the same size. So it is highly expensive, but still it is a very nice model. So for small, highly valued data, it can be used. So so the goal became that, okay, so now let's try to see whether we can convince everyone that this is a practical system that is of interest, and people should be interested in using this, especially because it's information theoretic, post-quantum. It is future-proof. If you capture the transcript, you cannot do offline attacks. So these are really nice properties of this system. So again, we worked on this for another 6 months, and then we wrote a paper, and that paper was rejected. And so there were lots of criticism from program committee that a lot more details of implementations were required. And I think that maybe the most disappointing statement that was in the review was that this paper has little to do with quantum safe security, because I guess it did not have computational assumptions, so they thought this is not quantum safe secure. So I think that was the end of it. So we thought actually that our system and networking colleagues were really, the amount of details that was required from program committee to make the implementation was just, so another 3 years of work. So it seemed that we have completely failed with everything, and at that stage we started looking at our experiments that we had done. And this observation that we had seen way before, that we had noticed that the length of the path is important in these systems. But we had ignored it. We thought because we were focused on our main goal, that was finding the cost. So we had not considered that. But if you think about this, so when we have a share that is on this short path, it has one chance to be captured. But if a share is sent over a long path, it has 3 chances to be captured. So at that stage, we thought, okay, so this gives us a is a side channel in this system. So the length of the path is an important parameter of the system, which is not captured in the wire model of communication. So that is where we have started looking. We call this one because there is a network data remnants attack in storage systems. So this is what, actually this is data remnant attack in the storage system. So we call this one network data remnants attack. And the idea is that data stays in the network and can be captured by the adversary. So if you look at it, the simple case of a 3-3 secret sharing that we have in this system, you can see this is how the data travels in the network. And you can see that if we see that the attacker captures the top 3 in the first time slot, it has captured 2 of the 3 shares, and the next time slot, it can have all of the shares, and the system completely fails. So really, SMT system, if in this model, if you implement them in a model like this, if you analyze them, they will be really that wire model is not going to work. So we did the analysis, and so this is, we did spend some time analyzing this, and then also propose some countermeasure that makes the attack less prominent like this, and that is what we published in NDSS last year. And as you can see, the list of co-authors is quite long because these are the students and postdocs who worked on all these different implementations that effectively all of them failed, but it led us to come to this conclusion that there is a side channel in the system. So this side channel is realistic. So there was a follow-up work that has shown that uses this side channel in these 2 spread and HS spread. So this is a follow-up work that shows that this side channel can be used to break real networking protocols. As I said, the side channel is not SMT, it's not theoretical, but also all multi-path routing protocols that use this wire model that assume one hop, one chance compromise of a wire. So in all of them, it works. So finally, I guess, so to just reflect on what we have done, so it was the outcome of research, as hopefully you have noticed, was quite unexpected. It took 3-4 years, and that's why we thought it's important to share our experience, because it took a long time to go through all these implementations with a lot of work, and all of them failed, and only just as a reflection of the results, we could find this side channel attack. The importance of implementation, I know that we are talking about implementations. Everyone realizes that theory is crucial, but also implementation is essential to see whether those models are really useful and can be used in practice, and what do they say about real systems. This becomes essential, very crucial in physical layer security. So as soon as we start abstracting the real world through this as a basis of our system, then we really need to have an implementation. And as I said, implementation can be different platforms that we can use. So we use software-defined networking, but if we had implemented this over the internet, it would have been a completely different result. So really, even in terms of implementation, the underlying technology is going to affect your final result. And so the importance of vetting the assumptions that you are making in the particular environment that you are implementing the system. In our case, we knew that when you have a software-defined networking, you are sure that the path is going to be followed. You cannot have this assumption in internet. Internet, you don't know where the packet is going, but in software-defined network, you do have this assumption, but then there are other problems that you have to deal with. So what are the underlying networks for software-defined network? And I guess the need for collaboration with other disciplines, it made it very clear to us that even if we have a student who can do the implementation, the real networking expertise was required to do this more clever implementation of routing, so that completely showed that you do not have a cost in software-defined networking. So you really need expertise in domains to collaborate together to have a realistic assessment of a system. I think that's the end of my talk, but I just thought I should finish with these quotes. So I mean, the abstraction, so we know that any system that we want to analyze, we have to make an abstraction. And so abstraction is the backbone of computer science and a starting point. And this is not computer science, but also earlier sciences, like what Lord Kelvin is saying here. But how relevant these models are and what they can say us, how much they can say us, that is really something that needs a lot more thinking and careful look at particular problem. And with that, I guess I just finished my talk, and thanks for listening.
Thank you very much. I think we're going to hold questions for this offline.